Hope you enjoyed the lunch. And today we're going to continue the session from yesterday on neural operators. That was the outline. And basically, yesterday we focused on the methods part and we talked about architectures, starting from DeepNets and graph and Fourier neural operators. And then we sort of tried to motivate this type of architectures that operate on functional data from two different perspectives. One is a dimension reduction perspective, and the second one was as tools that resemble what is called neural fields in computer vision. And that sort of motivated us to build new architectures and see things from a more broad point of view. So today I'll have two remaining parts, and I'll try to focus more on applications. Since the whole workshop is about design optimization, I'll try to talk a little bit about the applications of neural operators to design optimization. And one of the key elements there is the aspect of uncertainty quantification, because when we're thinking about using these machine learning tools for design, immediately you might think of things like active learning or Bayesian optimization, and the quantification of uncertainty is a key element there. And then in the second session, I'm going to focus more, I'll just give you snippets of more recent works on using those tools to build surrogates for PDE solvers, actually doing Bayesian optimization with these uncertainty estimates that we can get, and then maybe some details on possible routes to handling more complex geometries and things like that. All right, same format as yesterday. Feel free to interrupt with questions. Same goes for everyone online. Just unmute your microphones and jump in. So let's get started on uncertainty quantification. So let me start by just giving a taxonomy at 10,000 feet, at a very high level, of tasks that we might encounter that involve uncertainty quantification. Starting with a very simple task of here's a bunch of data points from some data set, x1 to xn, and maybe these are very high dimensional data points. It could be images or solutions on a PDE, on a mesh, maybe for different geometries, 1 to n. And one uncertainty quantification task to ask is, okay, all those realizations were generated from some underlying probability measure. Can I actually approximate that probability measure? Can I quantify the likelihood of these n observations? And then maybe further, could I actually sample and generate new samples out of that probability measure P of x? So that's sort of a density estimation task, if you wish. And because the fact is that in many cases, those data points will be high dimensional, there's going to be also a notion of dimension reduction embedded into this task for solving it. Similarly, you could have data sets that contain pairs of observations, inputs and outputs. So you have pairs x1, y1, all the way xn, yn. And you may now, in a similar fashion, be interested in recovering conditional measures. What is the probability of the output given an input? So you might have some random variability in the inputs that generates random outputs, and you want to quantify this conditional relationship between the two. Another task is that you could have a model, like a PDE solver or some surrogate, and maybe you have uncertainty in the inputs to that model. So the inputs are distributed according to some measure P of x. And now you want to propagate the uncertainty through your model, capital M. So you want to be able to quantify the distribution of your outputs given these random inputs, which is the probability of the model outputs as a function of the random input variable M. Yet another task that we might encounter is that we might have models that are parameterized by some set of parameters theta. They contain some free parameters. And those free parameters need to be somehow calibrated on data that we have observed. So let's say you have a climate model and you have a bunch of free parameters that you need to calibrate. So now you can collect weather data from weather stations, which is your data set, with n data points. And you would wish to now try to do parameter identification tasks, try to find what is the best parameters that explain your data, which in statistical language that translates to inferring a posterior distribution, as we call it, of the parameters given the data. So you might want to get a point estimate that these are the best parameters, but also if you want to care about uncertainty quantification, you would want to get the distribution of all probable parameters given the data, all right? And yet another task is that you might, since now, maybe you have a model and this M is a forward PDE solver that has some free parameters that need to be calibrated on data. You might also wish to know what happens if I use this PDE solver for a given set of parameters? How does the uncertainty in the parameters theta propagate in the solution of my PDE model? Okay. And that's another task in which, again, you have the model, you have a data set that you're going to use to calibrate your parameters. Hopefully, you have access to some posterior distribution over the parameters. And now you want to see how the uncertainty in the parameters propagates into the outputs of your PDE model. And to do so, this type of distribution is called a predictive posterior distribution, is typically expressed as an integral over that posterior measure. So you need to basically try to integrate out all the randomness in the parameters theta in order to quantify the probability of the outputs of your model. All right, so here I'm going to draw a line and kind of separate all those tasks into two big subgroups, because the group that you see on the top hand side is associated with what we call aleatory uncertainty. So this is by aleatory uncertainty, we mean uncertainty that is inherent to the way we measure the world. And it's a type of uncertainty that is inherent to the data that we collect and cannot be reduced. No matter how much data you collect, you could always have aleatory uncertainty because the nature of the data is random. The data could be corrupted by measurement noise. There's nothing you can do about it. And you just have to find ways to deal with it or quantify it. On the other hand, you have what we call epistemic uncertainty, which more relates to the uncertainty we have about the model parameterization, that very much can be reduced if we observe more data, if we have more power to calibrate those parameters, or if we have better models that can fit those data very accurately, and the uncertainty in these model predictions can be reduced. So epistemic uncertainty is something we can control by building better models and by collecting more data to calibrate those models. All right? And we're going to visit both of those categories because different tools are needed to quantify aleatory versus epistemic uncertainty. All right, so it's important to have this distinction in mind as we get started. Any questions so far? Okay. All right, so two different categories, two different sets of tools, and we're going to cover those in the first 45 minutes. All right, so before I go to the promise of deep learning, let me just say that, that all those tasks can become extremely challenging to solve if the underlying data that we observe is complex. It's very high dimensional, for instance, images or time series or solution of PDEs, which are infinite dimensional functions and so forth. So the challenge of solving these problems primarily has to do with the fact that we often have to deal with very complex data modalities for X and Y. And also we may have to deal with complex models M that transform an input probability distribution to some output probability distribution in a complex way. So maybe the output probability distribution has multiple modes or it behaves in a weird way. And we may also have to deal with models in which the number of free parameters is very large. So for instance, if M is not a PDE solver, but it's a neural network surrogate, then theta are all the parameters of the neural network. So that could be in the millions or billions with modern deep learning architectures. So essentially, this is what's called the curse of dimensionality. So doing uncertainty in these settings where you have to deal with high dimensional data modalities and large models becomes very complicated and expensive. But there comes the promise of deep learning, because deep learning gives us a set of architectures that allow us to process and manipulate this complex data modalities, starting from computer vision type of architectures on images or volumetric data, all the way to this more fancy generative models, like we talked about neural operators. So deep learning gives us some tools to deal with complex data modalities, with graphs and images and continuous functions and so forth. So we're going to see how we can use deep learning tools today to basically address or try to address both the part of aleatory and epistemic uncertainty quantification. Okay, more architectures for text and for continuous functions. So basically, this is where we left things yesterday. And today we're going to start with the aleatory uncertainty part. And in most cases, in the applications, I guess, that we're interested in, we have to deal with pairs of observations. So we observe some system state, and we have joint observations of inputs and outputs. Let's call them X and Y. So for instance, the input could be the state of the weather today, and the output is the state of the weather tomorrow. And we can just sample random pairs from some underlying joint distribution between states. And then our goal will be to see how the uncertainty in the inputs affects the uncertainty in the output. So primarily our goal will be to quantify this conditional here, P of y given x, okay? And again, if we're in this setting and the y's and the x's are indeed weather states, you can imagine that they're super high dimensional. If this is a PDE model, you have to consider all the grid points on the Earth for all the time steps. So extremely high dimensional data modalities. All right, so since we're dealing with high dimensional data modalities, at some point we have to consider dimension reduction techniques. And the only hope to solve this task of estimating P of y given x is only if there is some latent low dimensional structure to this problem that we can exploit in the way y and x are related. So that brings us to the realm of generative models that have a flavor of dimension reduction to them. And now we're going to talk about techniques like principal component analysis or variation autoencoders, which are both two different classes of generative models. And I can write them in this very general form that you see on the top. So the premise of building a generative model is basically to assume that your observed outputs are generated by some decoder function, let me call it D, that takes as input x, which is the input, plus some latent factor z that we don't observe. And that z factor is a random variable, and its role is to capture the variability in the random outputs y. But also the key fact here is that z will be of much lower dimension than x and y. So z are the latent variables that sort of capture the low dimensional structure of the problem and explain somehow the variability in the outputs we observe. So typically x's will be some random variables distributed according to some input distribution P of x. And these are some latent variables for which we have to choose a prior distribution that may sort of encapsulate any prior knowledge we have about the problem. And it could be something as simple as a Gaussian distribution. And then with this form in place, our goal is to estimate this conditional of y given x, which you can write it down as a mixture, as an infinite mixture of some likelihood of y given x and z, and then some prior that captures how z and x are related. All right, so that's the general form, and let me give you some example, and this is sort of the sketch of how this is going to look like. So finally, our models are going to look like autoencoders, in which a joint pair of x and y is compressed to some latent space of dimension n, and then through an encoding map. And then a decoder is decompressing the latent state z to the output observation. And to make things probabilistic and to make these models generative, we're going to place a prior distribution over the latent space that will allow us to sample that latent space and generate many different outputs, which in return will allow us to quantify the marginal, or sort of the likelihood of y. So we'll be able to actually estimate a probability density for y. Okay, so now we have to make some choices. We have to make some assumptions. And the assumptions is really how do you parameterize the encoder and the decoder, right? So the simplest way you can go about it is to let them be linear maps. And then you get something like PCA or probabilistic PCA. So if your encoder and decoder is a linear function, that basically, you just have a projection matrix W. And then if you choose your priors for your input space and your latent space to be Gaussian, you get a model called probabilistic principal component analysis. So it's basically principal components with this probabilistic flavor, because now you're working with probability distributions. So nothing fancy there, and you have everything is in closed form. You can derive everything in closed form because you have a linear model. You have everything is Gaussian, so that admits analytical solutions for posterior distributions and then everything else you might care about. Now, if you take a step further and you kind of go beyond linear models, and instead you start thinking about using neural nets and parameterizing your encoding and decoding map using more complex architectures, you can get something similar to a variational autoencoder. Again, if you still keep the Gaussian assumption on P of x and P of z given x, then you get something like a variational autoencoder. I'm not going to go into the details to explain what a variational autoencoder is. I guess some of you have heard of this, and many of you may know exactly what that is. But just for now, let's stay at the point to say that it's a generative model. We can derive an objective function for it to train it, and we can recover a nonlinear encoding and decoding map that will do this dimension reduction for us and will allow us to estimate this probability, but also generate new samples out of that conditional probability. And of course, we have to make some approximations. Things are not analytical in this case. So the key object of interest in all this business is to try to find the posterior distribution of the latent variables given the data. That basically answers the question, what is the best compression? What is the best set of latent variables that summarizes my data set? And in the nonlinear case, you cannot analytically derive it. In the PCA case, you can derive it. And it turns out that are the eigenvectors of your covariance matrix. In the nonlinear case, you cannot derive the posterior over the latent variables. You have to do some approximations. You have to do some approximate inference to retrieve it numerically. All right, so this is the tools out there for solving these approximate inference problems. One is by employing variational approximations, so trying to build some family of approximating distributions that are going to capture this posterior for you, and then deriving some objective functions. So these approximate distributions will be parameterized by some parameters phi, which are called variational parameters. And then you can derive some objective function for training and identifying what those parameters are by trying to minimize the distance between your approximate posterior and the true posterior. And one notion of distance between probability measures is the Kullback-Leibler divergence. There's many more, but sort of like one of the most popular choices in the literature. So you have to do a little bit of math. You have to come up with some lower bounds. So at the end of the day, you get an objective function that you can train with gradient descent and find all those parameters, right? A second class of methods that allows you to train this type of generative models is adversarial methods that take a different route by introducing a discriminator function. In a similar way, the discriminator is trying to approximate some notion of a distance between probability measures, but is doing it by comparing samples that come from those measures. So there's a trick in the machine learning literature called the density ratio trick. So if for those of you who know how to write down a KL divergence, it involves a logarithm of the ratio of two densities. And there's a very simple trick if you want to estimate density ratios in statistics, that you can draw samples from the two densities in the ratio. And then you can train the discriminator to discriminate whether a sample came from one density or from another. And that gives you an approximation of the ratio. This is really what lies in the heart of those adversarial methods like GANs and, stands for generative adversarial networks and so forth. So the idea is to introduce this auxiliary network that's called the discriminator that allows you to approximate these density ratios and minimize this probabilistic training objectives for building your model. I'm not going to go into more details. There is an excellent book on this topic. It's the current Bible of machine learning. It's a new edition of Kevin Murphy's book that basically has everything you need to know. That's what I tell my PhD students to read in their first year. If they want to eventually get a job in Google, they have to know those books inside out. All right, so we talked about neural operators yesterday. The one question is, do all these tricks and machinery extend to this setting where now our data lives in function spaces? And the answer is yes. You have to be a little bit careful with the math and how you generalize probability measures to function spaces. Things become stochastic processes. Again, the discussion can become really technical. We have an ICML paper that was recently published. We call it variational autoencoding neural operators. Basically, the paper describes the math on how you can take neural operator architectures and turn them into generative models in function spaces. And the whole sort of magic was that you can derive an objective function for training those, which is consistent with the fact that your data lives in a function space. But again, there's a lot of technical mathematical details that I don't want to bug you with at this point. But the answer is yes, you can do it. You can take neural operators and turn them into generative models. And here are some of the benefits of doing that. And again, it has to do with this whole resolution invariance that we were talking about, that you can query a neural operator anywhere you want, and you can therefore generate samples at any arbitrary resolution, or you can train it on training examples that come from different resolutions. So for instance, you may be familiar with VAEs, and maybe some of you have trained the VAE on the MNIST dataset to generate handwritten digits. But in the classical VAE case, you must have a fixed image resolution for the entire training dataset, and then you will only be able to generate new images at that fixed resolution. Whereas now you can build a model that is much more flexible with respect to the resolution of the data, both in terms of the training data that it sees, but also the samples that it generates could be in arbitrary resolutions. So in this paper, we had some examples, starting with some toy data sets. So let's say you have a data set of the circular bumps that basically are just 2D Gaussian densities, and then they come at resolution, let's say 48 by 48 during training. You can train your VAE, but then you can generate new samples at any arbitrary resolution that you want. And also that example was pretty nice because we used it to compare linear versus nonlinear decoders. So like the DeepONet version of the architecture versus a nonlinear decoder version of the architecture. And also you can see the same problem there, that the linear decoder fails to really do anything because we have a very slow eigenvalue decay in this data set. Similarly, another example coming from a PDE system, the Cahn-Hilliard system for phase separation. Again, you sort of see that the model can fit the data, can generate new interesting samples at arbitrary resolution. And the final row was actually real satellite data that kind of measures the deformation of the surface of the Earth due to landslides and earthquakes. And actually, it's extremely noisy. So the interesting part is that these models also help you to do some denoising of the measurements. So you can denoise the inputs, or you can generate new samples that have very similar distribution as your inputs. And you can extend this to make those models conditional. So here we're just estimating P of X. So going back to my taxonomy slide, it was the very first line. Here are some images. Can you now build a generative model for the density P of X and generate new samples? It's very straightforward to tweak what I showed you to now apply it in the case that you have inputs and outputs, and you're estimating P of Y given X. You get a conditional variational autoencoder instead of a marginal one. So that sort of captures the part of aleatory uncertainty. Either, if your data is finite dimensional, you can use things like VAEs or diffusion models. If your data is functional and lives in function spaces, you can do something like this. So you can do aleatory uncertainty quantification in infinite dimensional spaces, essentially, through these tools. All right, so going back to this slide, we sort of covered the top part of the slide on aleatory uncertainty. I didn't talk much about the last setting, but it doesn't really differ because it's very similar to the middle one. Now the outputs are some outputs of a model, but you can think of this M of X being your Y, and then you build your conditional variational autoencoder or something else. But again, let me go back to the comment I made earlier, the distinction between epistemic aleatory uncertainty, and specifically the fact that aleatory uncertainty is inherent to the measurements we could collect, and we cannot do anything about it, whereas epistemic uncertainty can be reduced by collecting more data. And epistemic uncertainty is the crucial mode of uncertainty when it comes to decision making. Later on, we'll talk about Bayesian optimization. This is really the uncertainty you want to be able to capture when you want to make decisions and collect more information and more data. So let's talk about epistemic uncertainty for the next couple of minutes. But before doing that, let me give you a very toy picture of how you can distinguish. What does it mean to distinguish between aleatory and epistemic uncertainty? All right, so here's a data set in 1D. And you have some measurements. So these are the green dots. And then you fit some model to those green dots, which is the, I guess, this dashed curve. What do we have to deal with here? What is this an example that is the aleatory uncertainty the part that would concern us, or the epistemic uncertainty? Any thoughts? What type of uncertainty do you see in this picture? Okay, that means I did a really poor job explaining what the two things are. Correct. So it's not epistemic uncertainty, and it's not epistemic uncertainty because we have a lot of data and we have a model that is flexible enough to fit the data correctly. So basically, we are recovering the underlying sort of clean signal, but we have to deal with aleatory uncertainty because the data we observe is very noisy, and there's nothing we can do about it. The more data we collect is going to be equally noisy, right? So this is a case that we're dealing purely with aleatory uncertainty. How about in this case? So this is purely epistemic, right? So we observe some data that is perfectly clean, and there's no uncertainty about the data, there's no noise. but there's a region in the space where it don't see any data, and our model should be uncertain about it, what it predicts. And you might say, okay, that's a stupid model, that's a sign function, there shouldn't be uncertainty in between, but no, you have not observed any data. How would you know what happens in the middle? So ideally, you wouldn't want a model that tells you, I don't know what's going on here because I haven't seen any data. And the only way you would hope that this uncertainty shrinks down is if your model had some inductive bias or some prior that kind of told it a priori that, hey, you're looking for periodic functions or things like look like signs. If you don't have such an inductive bias, then you should, it's desirable to see large uncertainty in this region that you don't have data. Okay, so that's the other extreme, that you have purely epistemic uncertainty, but then in reality, you have to deal with both. Okay, in practical settings, you collect data that it could have inherent randomness or noise, and you don't collect data everywhere, so you have regions where your model will have epistemic uncertainty. Okay, so now there's a funny thing about neural nets when you train them using standard objectives like a log likelihood or a mean squared error. And the funny thing is, conventional neural nets are not able to distinguish between those two modes in the predictions that they make. And let me give you let me try to convince you of that by a classification example. So let's say you're solving a binary classification task and you have two classes of images. You have images of rabbits and images of ducks, all right? And you cannot see clearly the slide. Hopefully we'll buffer and clear up. But now there's the two regimes. You have the top regime where you feed now, you trained your classifier, your neural net or whatever, deterministic classifier on these inputs. And now the output of the classifier is the class probabilities associated with the input, right? So it can predict some class probability for the duck class or the rabbit class. And let's say now you train the model and you're feeding a rabbit as an input, and then your neural network or whatever model gives you an output that says it's half and half, 50% rabbit, 50% duck. Well, it's kind of clear in this case that this is uncertainty due to lack of knowledge. This is a clear image of a rabbit, and the model, well, not so clear to your eyes, but it should be. On my slides, it's clear. If the model had seen enough of those two classes and it has the approximation capacity to kind of disentangle and feed a classifier, then it should be confident that this is a rabbit. So this is uncertainty now due to lack of knowledge. Our model hasn't seen enough data, was not able to kind of distinguish between the classes, and therefore there's uncertainty due to insufficient knowledge or training data. That's inherently epistemic uncertainty. So our model is just not good enough. Whereas in the second case, you have this ambiguous image that you cannot clearly see, but you see it one way, it looks like a duck, the other way it looks like a rabbit. It's kind of a funny illusion. And in this case, no matter how good your model is, it may well be confused, and it still gives you a 50-50 chance between the two classes. But this is really uncertainty due to ambiguity in the inputs of the model. So call it noise, call it stochasticity, ambiguity, it doesn't matter. And this is an uncertainty you cannot really do anything about. So that's aleatory uncertainty. Now, the problem is, once you have a neural net and it gives you some prediction like this, you don't have a way to distinguish whether that is aleatoric error or epistemic uncertainty. So you have to do something more to actually be able to distinguish between the two. All right, so let's see. So the elephant in the room is really epistemic uncertainty. So the aleatory part is really, to some extent, handled well by all these classes of generative models, diffusion models, VAEs. I mean, the ML community has made a lot of progress in building generative models that capture this aleatory part. But the epistemic part on how you quantify epistemic uncertainty in deep learning and these large neural network models, it's a much harder task to tackle. And that really has to do with the fact that those neural nets have millions or billions of parameters. And to quantify epistemic uncertainty, you need to be able to estimate or approximate the posterior distribution of P of theta given the data set. And that's a really, really hard task. So that's in the case of neural nets, because of all the redundancies and symmetries, you have, the posterior is very multimodal. It lives in really high dimensions. It's very ill conditioned. So it's very similar to the complexity of the loss landscapes of neural nets. So it's really hard to do any sampling or explore those distributions and generate samples. All right, so now when it comes to epistemic uncertainty, the standard tools of the game are, well, before I go there, let me just revisit the two tasks. One, remember, is again, parameter uncertainty, which is basically estimating the posterior distribution of your parameters given some data. And once you have the posterior, you can talk about predictive uncertainty, which quantifies the uncertainty in your predictions due to uncertainty in the model parameters. So basically, you have those two pictures here, right? On the left-hand side, you want to quantify the uncertainty of your parameters and come up with a distribution over plausible parameter values. And once you do that, you have to propagate this uncertainty of the parameters to the model predictions and get a picture like this that quantifies the uncertainty in the model predictions. And the tools for tackling this in practice is generally two different classes of methods. Well, the slides are a little slow today. Namely, they're Bayesian inference techniques that you're just going to use Bayes theorem and try to either derive the posterior distribution by hand, which is impossible for nonlinear and complex models, or come up with sampling techniques to generate samples from this posterior or approximate. So things like Markov chain Monte Carlo techniques, Hamiltonian Monte Carlo, variational inference, and you name it. The other way out is through ensembles. So you just train a whole bunch of neural nets. Each one starts from a different initial guess for its parameters. You train it with gradient descent, and then the more neural nets you have, the larger the ensemble, and then you create probabilistic predictions by just averaging out the ensemble predictions, computing variances, standard deviations, and so forth. And probably that's the safest way to do things with neural nets. It's really hard to do Bayesian inference with neural nets. But of course, you have to pay the price. Now it becomes a computational resources problem, right? You have to train, instead of one neural net, you have to train 100 or 200. And it's okay if you're doing small things, but people cannot train 100 ChatGPTs. That's gonna be a little too expensive. So how do you now deal with settings like this? Well, people are trying to come up with smart ways of extracting uncertainty estimates that sort of also balance out the computational cost that it takes. But at the end of the day, there's a million different ways of getting uncertainties, and I think each one of you probably has your own favorite one. An important question is, okay, I have my own UQ method for epistemic UQ in neural nets. Maybe I like dropout, and you like Markov chain Monte Carlo, and you like variational inference. At the end of the day, how do we assess who's better? How do we assess the quality of our uncertainty estimates? And a very interesting setting, well, okay, speaking about favorite ways, currently that's my favorite way of getting uncertainties. Okay, so before I talk about the assessment, let me briefly describe what this is. So this is an interesting framework that was proposed by a couple of folks at Google DeepMind, maybe about a year ago. These guys are doing a lot of reinforcement learning and decision-making problems like contextual bandits and things like that, in which they need to, similar to Bayesian optimization, you need to balance correctly the trade-off between exploration and exploitation. And for that, you need good uncertainty estimates. But at the same time, they're dealing with large architectures, so they cannot afford to do ensembles. They have to come up with a cheap and dirty way to get good uncertainties. So what they come up with is something called the epistemic neural network framework, in which you take a base network, let's call it f of theta, and that could be a neural network that somebody else has pre-trained. It's a fixed thing. Somebody trained it once. It's a deterministic neural network. And basically, this is a post-processing pipeline that takes a trained network and tries to generate uncertainty estimates out of it for epistemic uncertainty. And the way this does, it introduces two more components to the prediction, something called an EpiNet, which has trainable parameters, and we need to do some training here. And then another part, which is called the prior network, that is fixed and does not contain any trainable parameters, and basically plays the role of a prior. It basically controls how your predictions behave away from your training data. And the whole idea here is that this EpiNet that you're going to train will receive your inputs, but in addition to that, it will receive these auxiliary dummy variables, let's call it epistemic variables or epistemic indices, which are random and are distributed according to some distribution P of Z. So basically, you take the inputs and you add some noise to them in some sense. And then this EpiNet will try to figure out how this noise is affecting the outputs. So for instance, if during the training of the EpiNets, for a given input example, if we find out that the predictions do not really depend on the epistemic index, namely you feed it different Z's, but the predictions don't change, the overall predictions of your ENN, then that indicates there is the low epistemic uncertainty. Your model is very confident. Even though you perturb it with noise, it always gives you the same answer. So that's an indication of low epistemic uncertainty. Similarly, if you're in a setting where you feed a lot of epistemic indices and every time you get a different answer, that's an indication of that the model has high epistemic uncertainty. So that's sort of a cheap way. Well, it's not entirely cheap, but it's cheap in the sense that your base network is fixed and you don't have to build ensembles. You don't have to run MCMC on it or anything. The only expense is that you have to train this EpiNet, which is typically a much smaller network in size, because oftentimes you may not even give it as input the input variables. You could actually give it some features that your main network has extracted. So if your main network has an encoder decoder structure, you can give it these bottleneck features as input, which typically is not very high dimensional. So this EpiNet is a smaller network that you can train with much less computational cost than your base ChatGPT model, let's say. And it will allow you to get uncertainty estimates. Now, the question is whether those uncertainty estimates are any good. How do they compare with other techniques for UQ? A very nice setting for comparing uncertainty estimates is this type of sequential decision-making tasks. It turns out that if you're able to produce accurate UQ, it kind of naturally leads to making good decisions in these sequential decision-making tasks. So these folks in DeepMind, they care a lot about reinforcement learning. So they have benchmarked a lot of different uncertainty quantification techniques in this type of problems. So you see here an example where they're doing basically reinforcement learning. So they're measuring the average regret over the number of samples they collect sequentially. And they have different techniques of measuring uncertainty in their neural nets, either using dropout or using an ensemble of neural nets. Ensemble plus is an ensemble of neural nets plus another randomized prior part. And then finally, this EpiNet. So they have been able to report really, really good results with this EpiNet idea, which kind of really balances the trade-off between computational cost for getting good uncertainties and the sort of the quality of the uncertainties that you get. So that's sort of my favorite these days, but of course that's up for discussion and there's personal bias and there's other good techniques. But at the end of the day, if you want to discover which technique is better, this is the right setting to benchmark things. All right. Okay. All right, so I think this is what I have for the first part. So are there any questions? Again, two different categories, aleatory uncertainty, that's covered by generative models. Epistemic uncertainty is a much harder problem, and there's a whole different ways of approaching it. EpiNets is one recent framework that sort of is computationally tractable. And again, measuring the quality of UQ is important, and this type of decision-making tasks is a nice playground or yardstick for comparing different methods. And Bayesian optimization tasks fall under this category. So if you're doing design and you're using Bayesian optimization, again, uncertainty plays an important role, and that's a setting where you can compare different models and different uncertainty quantification methods. All right, questions? Yep. So, okay, so this is something, this is a benchmark suite that people at DeepMind have developed. It's called the Neural Test Bed. They have a whole bunch of different benchmarks, primarily bandit type of problems or contextual bandit problems. But the idea is, simply the bandit problem, the way, 101 introduction to bandits is you go to the casino, you have access to 100 slot machines, and now you want to come with a policy, an optimal policy to maximize your rewards. Which slot machine are you going to choose? So that defines now an exploration versus exploitation dilemma, right? In the beginning, you're going to start sampling random machines, and then you're going to start collecting some rewards. And obviously, every machine has a different probability of giving you a reward, right? So your goal is, with as few trials as possible, to come up with a strategy that will maximize your reward kind of asymptotically. So you can either exploit, meaning pull the arms that previously gave you some decent rewards, or you can explore and visit new machines that you don't know what's going to happen, right? So this is the setting here, this type of bandit problems, and they just fabricate some synthetic bandit problems in which they are measuring the performance. So the setting is that you first collect an initial set of observations, and now your neural network is a surrogate that maps your existing observations to the reward. So it's a surrogate for predicting the reward function. And of course, you have uncertainty about these rewards because you have not pulled all the arms. And now you're going to use this uncertainty to guide you which arm to select next in a sequential fashion. So similar to Bayesian optimization in some sense, but in Bayesian optimization, the decision space could be continuous, or in the slot machine case, you have 100 slot machines, or a decision space is discrete. But they have a whole bunch of different examples in this neural test bed that are problems of this nature, and then they're benchmarking neural networks as surrogates versus something else as a surrogate, and the different uncertainty quantification techniques that are needed to balance the exploration versus exploitation trade-off. Does that make sense now? Okay, cool. Yeah. Yeah. Mm-hmm.
The fixed prior method, where does it come into play?
So the fixed prior node also takes the same kind of inputs. So X tilde here, it's either some features of the base network or some features plus the input. So it has the same architecture as the EpiNet, but you just initialize it randomly and you keep it fixed. You don't train it. And it acts like a prior, basically. So that introduces. So I also should say that both the EpiNet and the prior net are small ensembles. They're not just a single thing. So the prior net basically gives you some variability and controls how your predictions will behave away from the training data. Yeah. No, this is just an animation, basically. Yeah, that kind of illustrates this concept of using the uncertainty to select the next point. But this is for animation purposes. It's not a specific. I don't know the specifics of this of this little video. Yeah, it looks like a Bayesian optimization to me, just by looking how things are evolving. Like you see that the sampling then concentrates around the global minimum of this function. So some little animation I pulled from the internet. Other questions? Because the next thing I plan to talk about is Bayesian optimization. And again, the key point here is that for this decision-making task is the epistemic uncertainty that drives the decision-making, not the aleatory. The aleatory, you just have to deal with it. If it is a part of your problem, you have to capture it in some way. But when it comes to deciding where to sample next, is really the epistemic part. Because the aleatory part, think of it as noise in the data, right? So that will never go away. And let's say in this example, if the data points were really noisy, it doesn't make sense to trust the aleatory part in terms of selecting which point to sample next. It's really the epistemic part that dictates that decision. So if you want to do Bayesian optimization with neural nets, you really need to have a way of quantifying epistemic uncertainty in a reliable manner. Yeah. Not necessarily, but you could actually, the way you formulate the problem and you build your model, you can build it in a way that you can distinguish between the two. So you can see the predictions of your model and say this part comes from aleatory error, this part comes from epistemic error. Other questions? All right, so let's move on to the next part. So the next part is a small collection. It's a little bit of everything, but I'm going to try to connect to this and start from the Bayesian optimization part. And this is sort of the pipeline of this decision-making, sequential decision-making problems, right? So let's say now, let's go back to design optimization. We're going to start with some design space down there. So you have some, let's say it's RD, you have D design variables. And the way this whole workflow typically works is that you're going to generate some random initial designs. You can evaluate their performance through your PDE solver or some experiment. And typically that experiment is expensive, so you have to come up with a way to collect as few measurements as possible. So you create this small initial set of designs, then you go about training some surrogate model that eventually wants to learn a map between your designs and the target performance metrics or rewards or whatever. And then you want to fit the surrogate model in a way that you can quantify epistemic uncertainty. And in this example, indeed, you have two things, right? You have noisy measurements, that's the aleatory error, but then you also have epistemic uncertainty in these regions that you don't have any data, right? And this is the part that is going to drive the selection process of where you sample next. So for instance, you have really high uncertainty in this right-hand side of the function. And in the next step, once you have, so okay, step one, collect initial designs. Step two, fit a surrogate model with epistemic uncertainty. Step three, take that surrogate model with its uncertainty and formulate a so-called acquisition function. So that's a function that will assign some utility to new designs. So it will say this new design has high utility, so it's promising, or low utility, meaning that it's not promising. And essentially, this acquisition function is balancing that trade-off between exploration or exploitation. So it should take high values and assign high utilities either to designs that have high performance or high expected performance, according to my surrogate, or assign high value to designs for which my surrogate is extremely uncertain about. So for instance, in this case, something that is on the right-hand side of this domain. The model says, I don't really know what's going on, but it looks promising to me, so you should go sample there. So now we're transforming the original problem of optimizing over our design space to this new optimization problem of optimizing the acquisition function for selecting the next design candidate. And this is a simpler problem to solve. I mean, the acquisition functions behave in a weird and erratic way. They're very non-convex, but typically you have an analytic expression to evaluate them. You can take gradients of that. So you can do very cheap gradient-based optimization with multiple initial conditions. So that takes seconds, basically, to solve multiple times. And then out of all those multiple times, you pick the best design candidate that gives you the most sort of expected reward or expected high acquisition value. And then you augment that now to your training set. You take that design candidate, you're going to run an experiment, you observe yn+1, and then you augment that pair of observations to your data set, and you keep going sequentially. And of course, there's techniques that allow you to pick 2 designs at a time or 10 designs at a time, so multi-point acquisition functions, but that's a finer detail now. So you just proceed sequentially, either until you reach some type of convergence, meaning that your algorithm keeps sampling the same thing, or more often because you just out of resources, okay? You can afford 50 iterations of this process because your experiments are too expensive. All right, so this is Bayesian optimization in a nutshell. And again, the key point here is surrogates with quantify uncertainty, epistemic uncertainty. And the second key ingredient is the choice of the acquisition function. I'm not going to talk much about the choice of the acquisition, but I'm going to show you now some applications where this whole pipeline can become challenging. So I'm sure many of you are familiar with this. And I would say probably 95% of the current literature that employs Bayesian optimization for this type of design optimization task is using Gaussian processes as the underlying surrogate, okay, which is really nice. They have tractable inference. You get this nice posterior uncertainties, blah, blah, blah. But they're going to be hard to scale to data modalities that are complex and high dimensional. Like if your input space is high dimensional, you're in trouble. If your target outputs are also high dimensional, you're also in trouble. Or if you need to collect for some reason a lot of data, also you run into computational complexity issues. So now let's see, the question is whether we can use deep learning tools to maybe do better than Gaussian processes, or at least scale to more interesting problems. So here's an example of an interesting problem that maybe Gaussian process-based techniques struggle, but I'm going to use it as an example to kind of discuss at a more high level different ways of thinking of this problem. All right, so in this example, we have the following sort of design optimization problem. We have 5 radio signal towers. These are the red dots in those pictures. And for a given position of those cell towers, we can measure the radio signal power that is transmitted by each of the towers, and also the interference of the signal between the towers. And the design task that we want to solve is we want to optimize to find the optimal placement, the optimal position of those 5 towers, such that the overall signal coverage is maximized while the interference is minimized. Okay? So essentially, we have an input design space, which is the position of the towers in 2D. So we have a vector in R10, XY coordinates for each of those 5 towers. And then we have a final objective, let's call it C, that it's some real valued scalar that captures this objective of maximizing signal while minimizing interference. It's some integral over these solution fields. And then, of course, we have those solution fields, right? The power field and the interference, which could be the outputs of a PD solver, for instance, that are functions, continuous functions defined in some domain here from 0 to 40, and then returns vector valued outputs right in R2. So power is one output and interference is the other output. And now the objective is going to be computed through some deterministic function G, some kind of integral over U, over the spatial domain, to compute, the overall signal power and the overall interference, and then sum it up to a target objective that we want to optimize, right? Okay, and now the difficulty, well, let's see. If you were to approach this problem using Gaussian processes, what would you do? This is what I call option A. So in option A, you would try to learn a surrogate model that maps your design inputs to the target quantity of interest, which is the C variable. So it's a map from R10 to R. And then you'll try to find, using the surrogate, the optimal input, the optimal placement of the towers. But arguably, that could be a very complicated map. It's not super high dimensional from R10 to R, but the relationship between tower placement and the final scalar objective could be a little bit complicated to learn. You may need a lot of examples to learn from it. And also, it's unclear if this is a map that has some regularity structure that you can exploit. And of course, in the process of doing that, of trying to map the inputs to the scalar objective, you kind of throw away, you kind of throw away this intermediate layer, right? You throw away this intermediate representation, which is the full PD solution field. Like, you're not using it in any point of this process. I mean, you only use it. I'm messing up my slides, but okay. Yeah, you kind of get rid of this. So if I were to think of this little diagram as a neural network, I give an input in R10, and then I have this really, really, really wide hidden layer that is my power interference signal solutions. And then everything goes down to a scalar. Okay? And now if I'm to build a surrogate like a Gaussian process, I'm getting rid of this really wide hidden layer, and I'm trying to go directly from the inputs to the performance metric. So arguably, I'm throwing away some information. So option B would be a different approach and say, well, let's not build a surrogate from the inputs to the scalar objective. Let me try to build a surrogate from the inputs to the PD solution fields, which is kind of like a nasty problem. I'll go to R10, from R10 to a function space that is infinite dimensional. Or even if I discretize those PD solution fields, I would go from R10 to images with 2 channels, so high resolution images. So that's going to be arguably nastier surrogate to train, and maybe you think you need a lot more data. But let's say we have a way of doing that, and then finally you can get the optimal design by now minimizing this objective. So your surrogate maps you from the inputs to this use, and then there's a deterministic function once you have the use, right, to get your objective. Once you have the PD solution field, it's a deterministic map that that part you don't need to learn. Okay, so now basically if you were to contrast option A and option B, in option A, you sort of have to, sorry, I keep messing it up. In option A, you would have to somehow disentangle how this G function it's a composition, right? What you're trying to learn with your surrogate is a composition of those 2 things somehow, in some sense. And your model is asked to figure out, to somehow learn that composition or disentangle the effect of this G function. Whereas in option B, you kind of more explicitly take into account that you have this first step of going from inputs to PD fields, and the second step that this deterministic function a priori, you don't need to learn it to get your performance metric. But the problem now is that you cannot really use a Gaussian process to learn this type of surrogate, right? You have something with extremely high dimensional inputs. Well, it turns out if your inputs live on a grid, there are some tricks in the Gaussian process literature. You can do things with FFTs. You can do things with Kronecker products and smart linear algebra. So there is ways of fitting a Gaussian process in a setting like this, as long as you have discretized your solution fields into images, equispaced, basically grids. So recently, we kind of wrote a paper that we compared these Gaussian process-based approaches that can work in the setting if you have images, basically, versus a neural net approach, which is not the epistemic network stuff that I showed you earlier, but it's a simpler variant of that, which we called randomized prior networks. And here you see performance sort of results for two different benchmarks. The benchmark on the right is a PDE system. It's a control problem. The PDE is a Brusselator PDE. That's how it's called. You have 4 input control parameters, and then the output space, the PDE solution field, is discretized to have 8,192 pixels. So it's high dimensional. So that's a setting that is specialized GP tools can work. And the dashed lines is the performance of the Gaussian process-based tools and some standard packages for Bayesian optimization. And then the solid lines is the deep learning convergence using different architectures and different acquisition functions. So MLP stands here for multi-layer perceptron to parameterize this map from R4 to R8000. And then DeepONet is the DeepONet that we talked about yesterday. And again, the surrogate now that we're learning is a map from the input variables to the function space. And then from the function space, we have a known objective to get a scalar objective that we optimize. So this function G here is something known, and we're learning this surrogate f of theta. And then maybe one could think that, okay, how can this be possible? You only start, our initial training data set was 5 examples. So we solved this PDE 5 times, and that was the initial set of data. And then from there, we did Bayesian optimization where we acquire 1 example at a time at every iteration. But also, these are 5 examples, and the network could overfit, but you also have this posterior estimation, this posterior uncertainty that is going to drive where you sample next. So this is the key point here. Like your network doesn't have to be the most accurate network, or it could be accurate in the sense that it overfits, but as long as you get reliable uncertainty estimates, that will drive the good decision making of where to sample next. Yeah. No, you only train for F. You don't backpropagate through G. You train F. Once you have the outputs of F, you evaluate G, which will give you a scalar objective. And then also you can propagate the uncertainty of F through G, because G is a deterministic map. And you use that uncertainty to select the next point in a Bayesian optimization setting. Yeah. Yeah. Correct. We don't have a problem of the Kronecker rule. The problem that we do have is now that we have neural nets as a surrogate, and we get these ensemble predictions for the uncertainty part, we don't have a closed form expression for evaluating the acquisition functions. Because in the GP case, everything is analytic, right? You have a nice expression for expected improvement or the LCB. Now we don't have a closed form expression, but all the acquisition functions, or most of them, can be written as an expectation over something, which means they can be approximated through Monte Carlo samples. So we take the ensemble outputs and do a Monte Carlo approximation of the acquisition function to evaluate it. So that's one technical catch here. But that's fine. That sort of, it works. Yeah. Right. Yeah.
Like this. That these types very close to the problem I have.
Yeah.
Currently.
So I think we've gone up to maybe, there's another example in this paper that is doing kind of turbo machinery blade shape optimization. And I think it's up to like 30 or 40 parameters. But the whole point here is also that you can use this type of operator learning architecture. So even your inputs could be functions. And as we said yesterday, the operator learning will kind of do some automatic dimension reduction for you. So I'm hopeful that as long as you can train a neural operator, as long as you can sort of, you should be able to do something with it. So the catch is, yeah, to kind of be able to train the neural operator and get uncertainty. If you're able to do that, then certainly this framework will give you a way of sampling new designs, and then hopefully you'll see some convergence. This example is a little bit more interesting in the sense that the input space is also not very high dimensional, but the output space is high resolution images. I think the resolution is maybe 256 by 256, and there's 2 channels, so it's 65,000 dimensional. And if you choose to discretize, if you take the operator learning approach, you don't even need to discretize, so your output space is really a space of functions. And again, you see the dashed lines are the GP-based approaches from the Maddox and Wilson paper, and then the solid lines are the neural net sort of convergence as a function of the number of experiments we run and the function evaluations. Other questions? Yeah. So here, essentially, we don't do option A in the sense in both the GP methods and our method, we're learning this map from the input space to the PD solution field. We haven't tried to train a GP that goes from the input space to the scalar objective for these benchmarks. That's something I did a lot when I was younger, and at least from my experience in other problems, not these ones, you need a lot more samples to get good convergence. Yeah. Mm-hmm. Mm-hmm. Yeah. I mean, yeah, the motivation is, yeah, that we don't want to throw away that information. Yeah. And if I go back to this slide, I have, my personal hunch is that for a surrogate, it's much easier to learn this part because, again, the variability in the inputs and the way that affects the change in the PD solution fields has a smooth kind of, regular structure. So it's easier to learn this part than learn the whole thing in one shot. All right. Other questions? So that's, I think, all I had in terms of Bayesian optimization. I'm going to switch to totally different topic now. Oh, no, not entirely different topic. So I'm going to ask if I'm going to pause and take a slightly different route to design optimization. And then, because you might think, why do I need to do that, right? Well, okay, why people do Bayesian optimization is because typically you have expensive experiments. You cannot really do many evaluations. So you start with a small set and then you kind of select one point at a time. Maybe if the cost of experiments was not so large, maybe one can say, well, I can afford to do 2,000-3,000 experiments. Here's all the data, take it, build a surrogate, and then use the surrogate to do optimization without acquiring more data. So let's call this surrogate-based optimization. So here's a simple example where you can use neural operators in the setting. Actually, physics-informed DeepONets in the setting. So the problem is a toy problem. It's extremely simple. So you have a Stokes flow, and you want to do shape optimization. You want to find the shape that minimizes the drag or minimizes the dissipated energy in the flow. So it's just a toy Stokes flow, steady state. And what we try to do there is we try to build the physics-informed DeepONet, meaning that we're not going to call any CFD solver to generate training data. We're going to try to train that neural operator using the Stokes equation as a PD constraint, like in a pins type of flavor. And our neural operator will try to learn the map from the shape geometry from this closed curve boundary, d gamma, to the solution field of the Stokes problem. So the UV velocity and the pressure. And it turns out it's really, really hard to do that. Like it took us a long time and kind of many iterations and tricks in the architecture and the optimization to just be able to train this physics-informed DeepONet for this toy problem. But eventually we were able to train it with reasonable accuracy with about 4 to 5% error compared to a finite element solver. And then once you're able to train it, then yeah, you can do shape optimization, right? Now you have a surrogate that maps from shapes to solution fields. You can take the solution field and compute the drag of the object, and then you can just feed the whole thing. Everything is end-to-end differentiable. You can feed it to a gradient-based optimizer, and this is it. And in fact, the compute time it took me to generate this animation is probably 10 times more than the time it took to actually do the optimization. It just takes 2 seconds to do the optimization. And you can see how the shape is changing. The initial guess is a circle and kind of deforms into an ellipse. So that looks cute and nice. But what are some issues here? There's quite a few. So what are some of those issues? What are the pitfalls of taking an approach like this? Obviously, one pitfall is arguably that you might need to call PD solvers to generate training data. Here we didn't. We were able to kind of do things in a physics-informed way, but that is difficult. So one pitfall is potentially you might have to call PD solvers and generate some data. What are other issues here? Yeah. Exactly. That is a main issue here. So nobody guarantees you that the optimal design is going to be among the training distribution that you use to build your DeepONet or whatever model. And it may well be the case, well, okay, if your problem is very well defined and you say I have 10 design variables and these are the strict bounds, then I can always generate training examples within the space and stay within the space. But if in some cases you want to be more flexible about the parameterization and it's hard to define that, it may well be the case that the optimal design is outside of your training distribution. And then things will fail because you're asking your neural operator to predict things that are out of distribution, and then you'll just get garbage predictions. So yeah, that's sort of like the question to pose here. Can you expect your surrogate to generalize? The answer is no. And what can you do? In what way could you use surrogate models in this setting for design? And I don't think I can see a different way of having to kind of update your surrogate as you go. So you have some initial distribution of designs, you train it, you make predictions, and then you kind of change the distribution of the designs, but then you have to change the model itself in an iterative way. So you can pose this whole thing as an adversarial thing where you have a surrogate model and a design generator that kind of, you generate new, so there's a distribution of designs that is evolving, and there's also the surrogate that is also evolving along the way. But it becomes messy, and I don't think you save any money compared to just using your favorite PD solver. So I wouldn't, yeah, there is a pitfall in terms of thinking in this way for design optimization. That's the thing that I wanted to bring up. And the other thing is kind of difficult, right? This is just a toy problem, and it did take a lot of effort. Imagine having to deal with things in 3D, more complex geometries. Quickly, things become even more hopeless. But yeah, I'm open for discussion. I'm just throwing it out there because that's where I got stuck, and maybe people have better ways of doing this. All right, so since I mentioned the word complex geometries, let me say a few things about them because probably some people are interested. How can we deal with complex geometries and at least within the realm of the things that I showed yesterday as well? And I know Matthias showed some interesting stuff with IGA earlier today. But now in the context of operator learning, there is two places where complex geometries introduce some challenges. First, if the geometry itself is an input to your model. So how do you handle, complex shapes and things like that as inputs to your deep learning model? One way of doing that is to use appropriate encoder. So the whole name of the game is how do you design an encoder architecture that can receive geometric inputs. And one way of representing geometric inputs is through point clouds or meshes. So you can think of building encoders using graph neural networks or types of architectures like this, which is called a point net that can process point cloud type of data. So this is one sort of area. If your input to the model is different geometries and you have complex geometries from one example to the next, you have to come up with proper ways of designing an encoder architecture that can handle this type of input data modality. So either graph neural networks or this kind of point cloud based permutation invariant type of models. The second part where complex geometries can enter into play is on the output side of things. You want to predict a function that takes values on a manifold or on a complex shape. So you want to build decoders that can, predict functional quantities of interest on complex geometries. And that has also possible solutions, but one solution that we have experimented with, and it seems that it works well, is by designing appropriate positional encodings for your decoder architecture. So yesterday I mentioned briefly let's say if you're using an MLP decoder, oftentimes people use Fourier features as a positional encoding to help the MLP learn functions with higher frequencies. You can use appropriate positional encodings that encode geometric information of the problem in your decoder structure. And the way that we did that in some recent work is the following. So let's say you're dealing with some complex geometry. You can take it and do some pre-processing by solving a finite element problem, or in any ways, could use different numerical methods, but the whole goal is do some pre-processing to approximate the eigenfunctions of the Laplace-Beltrami operator on that mesh or on that geometry. That will encode some distance, then some information related to the distance metric on your geometry or your manifold. And then you can use these eigenfunctions, which are pre-computed and known. These are deterministic functions. You can use them as a positional encoding. So instead of building, let's say, a traditional pin model, in pins we just give the coordinates as input to the network. Now, instead of giving the coordinates, we first take the coordinates, use them to evaluate these eigenfunctions, and give the outputs of these eigenfunctions as input to the network. And that allows the network to be aware of the geometry of the problem. So you kind of encode the geometry of the problem through this positional encoding. And by doing that, we show that you can actually use pins to solve PDs on complex shapes, manifolds, complex volumes, and things like that. So it's a simple trick. Of course, now that technical details are a little interesting. Of course, you have to pre-compute these eigenfunctions, which is not very expensive. It's just a single solution of an elliptic problem, basically. And then you have to also be able to backpropagate through those eigenfunctions when you're training the pin model or your neural operator. That gets a little bit more tricky, but it's doable. So for the details, you can look this paper with the methods called delta pins. So here's some examples of these delta pins. On the left-hand side, you see a solution of a Poisson equation on this complex statue geometry. So you have on the left-hand side, on the middle, you have the ground truth, the pin solution on the left, and then the source term on the Poisson equation plot on the right. And then the right animation is an operator learning problem where we take a DeepONet architecture. And now the decoder has to be aware of this bunny geometry. Our goal is to learn how to compute geodesic distances between any 2 points on the surface of the bunny. So we train a kind of like a physics-informed DeepONet to be able to learn this mapping. And you see now in animation, you have a bunch of geodesic distances between this fixed point and then other random points on the surface of the bunny, which is not a straightforward problem in computer graphics or vision to compute these geodesics. So now, you just train this DeepONet without training data, just a physics-informed type of constraint. And then at test time, you can really quickly generate these geodesics on this complex surface. So yeah, this is just a highlight of one trick of building decoders for these neural fields and neural operator models that are aware of the geometry of the domain that you're trying to predict on. Yeah. You can define kernels on the manifold. Yeah, so there are techniques with GPs. And actually in this paper, we have an example where we compare against Gaussian processes for some toy regression task. So yeah, there are Gaussian processes where you can define actual kernels that encode this manifold geometric information and use them, yes. Right. Other questions? Yeah. Yeah, so we train a neural network that learns to predict the inputs is any 2 points on the surface of the bunny, and the neural network gives you the geodesic between those 2 points. Yeah, so it's a neural operator. The inputs are basically the coordinates of the points, and the output is the curve on the manifold. Yeah. Correct, yeah. Yep. So there is an example in this paper where I think we do some kind of hyperelasticity problem, like a solid mechanics deformation thing. So, but I think that's all. Well, this is not really my work. That's Francisco Costabal and Simone Pezzuto. I mean, I was on that paper, but I just, blessed the effort. No, okay, I did a little bit of coding and helped them out to deal with some of the issues, but yeah. Right. On the surface. Yeah. But you could do it inside as well, but then in that case, you would have to get the eigenfunctions inside the geometry as well, right? You have a 3D volume mesh. So you pre-process, get the eigenfunctions on that volume mesh, and then use that to build your pin model. Yeah, the technical tricky part here was how do we backpropagate through the pin and the eigenfunctions and how we take derivatives of all that since we have a pin objective. So we had to use basically the finite element operators to approximate derivatives of finite elements instead of doing automatic differentiation. So that was the catch here. Other questions? All right, it's 15 minutes left, so I'm gonna switch to another topic. And that is the neural PD solver. So that's an area where probably most of the excitement currently is in terms of using this neural operator type of models and build surrogates to solve PDs and to PD solvers. I mean, the promise here is that, once you train those models, you can solve, I don't know, many PDs in seconds, right? Like starting from random initial conditions or other random inputs, you can integrate PDs very, very fast, like thousands of times faster than a PD solver. Okay, that's just a number I put there, but we have to be more careful how we do comparisons. But yeah, it's just faster than a classical PD solver. And in many cases, the way these neural PD solvers work is they kind of take discrete snapshots. You train them on pairs of system state at time t, system state at time t plus some lead time delta t. And you train them on many, many pairs of states. And then once you're done training, you can evaluate the model and you can unroll trajectories in time. So basically, you can solve the PD, but by recursively or autoregressive rollouts. So you take the initial condition, you feed it, you get the next time step as an output. Now you feed it that back to the network as an input, and then you get the whole trajectory in time. And you can also train those models with variable lead time. So another argument to the model could be the delta t. So essentially, you can predict at any future time continuously. Now, the problem is, and of course, that's always been a problem with time integration, is the stability and the accuracy. It turns out that those type of tools kind of learn a forward Euler integrator, and they're not very stable. Like this autoregressive rollouts can quickly diverge and push you off the right trajectory manifold. So how do we deal with this, or why does this happen? How can we deal with this? A lot of people have tried a lot of things, including doing things like implicit time integration instead of forward Euler, and still doesn't work. So there's a lot of open questions. Some work that we did recently, actually an intern at Microsoft did a few months ago, took a closer look into this problem and tried to identify why do we get these divergent trajectories and whether that can be improved. So one of the key issues that we found and we kind of used to attribute the difficulty of doing these autoregressive rollouts is the fact that these neural PD surrogates oftentimes do a poor job in approximating correctly high frequency components in the target solution function. So this is an example. This is the Kuramoto-Shevasensky equation. It's a PDE. It's a one-dimensional PDE, nonlinear, with this kind of nonlinear advection part and this nasty fourth-order derivative term. And if you were to plot the frequency, the solution in the frequency domain, and you see the spectrum of the solution, you kind of get a plot like this, where you have some low frequency modes that have high amplitude, and then there is a cascade, and then finally you have high frequency modes with low amplitudes. So that's sort of the ground truth distribution of frequencies in the true solution. Now, if you were to train a neural PD solver using a mean squared loss that learns to predict the next time step, even though we can actually build and train those models to be extremely accurate, to be almost reach machine precision in how accurately they predict the next time step, you can still see that if I plot the spectral decomposition of the prediction, we do a really good job capturing the low wave number, high amplitude modes, but they do a very poor job capturing the lower amplitude, high wave number modes. So basically, they overestimate the amplitude of the high frequency modes. And for one-step prediction, that's not an issue, so that you can still train them, and the one-step prediction will be very accurate. But the fact that we are kind of mishandling this high frequency part really kicks in and affects the long-term trajectory when you do the rollouts. It really messes up the accuracy of the trajectory. So for one step ahead, you're fine. Like the low frequencies are what matter most, but then the high frequencies start to kick in, and their role is increasingly more important once you're trying to simulate the dynamics further in time. Okay, so this is the solution that we came up with. And basically, it sort of throws away the mean squared error as a training objective. So basically, what we identified was if we train the model with mean squared error, it can achieve very, very low loss. But at the same time, we see this behavior of kind of neglecting or not capturing correctly the high frequency content. And to fix that, one idea that seemed to work very well and robustly was this idea of iterative refinement. So we introduced a class, which you can think of it as a new kind of a loss function, essentially. So, or a new type of model. I like to think of it more as a loss function. So we call it PD refiner. And the idea is as following. So now we have your neural operator that takes the solution at the previous time step and predicts the next. That was the standard MSC training neural operator. But now what we're going to do is we're going to introduce these auxiliary inputs. Let's call it U hat 0. Think of it as an initial state, and so U hat 0 could be just a vector of zeros initially. And in the first step, your neural operator will take those two inputs and predict the next time step. But then you're going to enter this iterative refinement process. So what you're going to do within this refinement block, you're going to take the prediction of the previous step, you're going to corrupt it with noise, and now this is going to be your new auxiliary input. And then you will also feed the solution from the true solution from the previous time step. So you feed the previous prediction corrupted with noise and the previous time step to the neural operator. And the goal of your neural operator now is to predict the noise that you added. So it's not predicting the next time step anymore. It's predicting the noise that you added. And once you get the prediction of your neural operator, you get the next time step prediction by subtracting that noise from the auxiliary input. So you're kind of deliberately corrupting this auxiliary input with noise, and then you're trying to denoise it. The neural operator tries to learn this denoising objective. So basically, this is the loss function. So now instead of trying to predict the next step, we're actually trying to learn the noise. So the objective function basically takes this form. And then there's a very important parameter here, sigma kappa squared, which is the noise variance. And that's something you have to carefully select. And in fact, you start from a large noise variance and then you decrease it to very small values as the steps of the refinement process go on. And the intuition here is that by adding noise, this noise effectively is going to mask different parts of the frequency spectrum. So large noise is going to really mask out all the high frequencies or even some of the low frequencies. And then smaller and smaller noise is going to only mask out higher and higher frequencies. So now you have this type of data augmentation that your model always sees. Even for the same input data point, you're going to see different versions of it corrupted by noise, in which this noise is kind of mask different parts of the frequency spectrum. And by doing that, it turns out that the model learns how to pay equal attention to both low and high frequencies. So its predictions improve considerably. The low frequency predictions are still accurate, but the high frequency predictions improve a lot, especially if you do a few steps of this refinement. And basically, this is how you train the model in practice. You're just going to sample an index k. So k is the index of the refinement step. So you're going to sample a k from a uniform distribution. Capital K is a hyperparameter, which is the number of refinement steps. So you sample a random k, and then for that random step, you compute this denoising objective. This is how you train the model. And again, the sigma k is a key variable here. The way you kind of schedule the noise variance plays an important role. And the way we have to schedule it here is very much different than how it's done in typical machine learning, because this basically resembles a diffusion model in the machine learning literature. So again, it's kind of, we're trying to learn a denoising objective. And then this noise schedule is important. So here we start. So little k is the denoising iteration, capital K is a total number of steps, and then sigma min is something, it's a very small value, like 10 to the negative 7 or 10 to the negative 8. So this is the noise schedule that we use. All right, so if you do this, you end up getting a much better, more accurate prediction in terms of capturing the low frequencies. Again, this is the plot to focus on the top left. The blue line is the ground truth frequency content. The orange line is what you get with a plain MSE objective that gets the low frequency, high amplitude part, but does a poor job in the small amplitude, high frequency part. And then this is what happens once you start doing some refinement steps. So 1 refinement steps, 2 refinement steps, you get closer and closer to the kind of ground truth spectrum. And now the cool part is this big table on the bottom, which is a really large ablation of applying this type of training objective to multiple different architectures in the literature. So Fourier neural operators and UNets and a whole bunch of other techniques that people have come up for improving this kind of long rollout prediction, something called the push forward trick. So using Sobolev loss functions. Yeah, there's a lot of tricks in the literature. So basically the really large scale ablation study to compare this tool to what's out there. And what you see is that consistently, this is the PD refinement results. So on the y-axis is the correlation time in which the prediction stays close to the ground truth. And you see that with this PD refinement objective, we can sort of extend this horizon in which the prediction stays close to the ground truth. And this is, again, for the Kuramoto-Shivasinski example, which is also a chaotic dynamical system. And this is the difference between using the schedule, the noise schedule that I just showed you versus the classical cosine schedule that people use when they train diffusion models. So yeah, there's a lot of information here that I'm skipping through quickly, but the message is that this works quite well. And yeah. Yeah. So here we use Gaussian noise. The nice thing with Gaussian noise is that it introduces no bias in selecting. Basically, it uniformly masks different parts of the frequency spectrum without biasing low frequencies or high frequencies. It's basically uniform in the way that it's going to mask out. Yeah. Yeah, it's like the simplest choice that works well without introducing bias. But how you do that, right? That's the question. So you're saying train a neural operator that overestimates and gives you high amplitudes for those high frequencies, and then do some post-processing to filter those out, right? Is that what you're suggesting? What you're suggesting is, let's say, let me not do this whole thing. Let's take a plain model that is trained on the mean squared error objective that gives you a spectrum like this, which basically overestimates the amplitude of the high frequency modes, and then manually later on do some kind of filtering to remove that. Right, but then how do you decide how this filtering should work? You have to, yeah, how do you decide the frequency? You have to tune that filtering process somehow without having any prior knowledge how to do that. I mean, in principle, it could work, but you have to very carefully design a filtering mechanism to do that. All right, so finally, the cool thing about this is that this whole process makes your neural operator a generative model because you're sampling random noise and then you're decoding functions. So going back to generative models and aleatory uncertainty quantification, you can generate now multiple trajectories. And the cool thing is that this gives you mechanisms for uncertainty quantification. So this is what happens for the Kuramoto-Shivasinski example. I think now you're saying on the top is the ground truth. The bottom is a prediction of this neural PD solver as we unroll the model in time. And here's a correlation between the ground truth, the cross correlation between the ground truth and the predictions. And on the bottom, actually, this is now about 128 trajectories or 64 trajectories. Anyway, some number of samples out of the model. And you see that all those samples stay close with each other in the initial time. Everything is very accurate and matches the ground truth. But this is a chaotic system. At some point, we're going to accumulate errors, inevitably. And you will see that at some point, all those trajectories will start to deviate from each other. And that sort of also gives you an indication that, hey, this is how far you can trust the predictions. It's time to stop. So this is like a very nice byproduct that you have this built-in sort of uncertain quantification that tells you up until which point your neural operator is confident about what it predicts, which is a nice thing to have, I think, for machine learning methods. All right, so I think that is all I have, and I'm a few minutes over time. I can take some questions. Maybe we'll have the break. So, yeah. Yeah.
K is equal to 0.
Correct.
K is 1 and 4.
Yeah.
Right?
Yeah.
If K is equal to 0, I try to predict
The next step. Right.
Any value K is 0, I try to predict.
Correct.
Right?
Yeah. And surprisingly, it works. We actually tried to separate that to the two architectures, and it didn't make any difference for the examples that we looked at. And in fact, this is a trick that also people in the diffusion models community uses. It's called the V prediction step, in which, again, they have a diffusion model that in one step tries to predict the output image, versus the other steps it tries to predict the noise. And I think if the architecture is sort of strong enough or expressive enough, here we did that with UNets, not with, well, we also did that with FNOs, but with FNOs, things are going to be horrible, as you can imagine, because eventually we need to predict noise, and the FNO is really hard in predicting things that are not very smooth. Exactly. Exactly, yeah, because of the cutoff in the frequency. Yeah. Mm-hmm.
If I didn't understand you say that instead K is random, so you are not going from 1 to K.
Yeah, so the way you train it, at every step, you pick a K from 0 to K uniformly, and then you evaluate this loss function. No. No, sorry. I think maybe I'm wrong. You repeat up until that little K. You pick a little K, but of course, to reach that little K, you have to perform those steps, right? Yeah. No, capital K is a hyperparameter. You choose that. Capital K is the maximum number of refinement steps. And then during training, let's say we're doing an iteration of training, what I will do is I will sample uniformly a little K from 0 to capital K. And then let's say I take a little K that is 2, for instance. So then I'm going to do 2 steps here, right? So you're going to start from the 0 step and you're going to go up to 2. Yeah. Mm-hmm. Yeah. Yeah. Sigma is much, yes, like 10 to the negative 7 for this KS example. Right. Mm-hmm. Yep. Mm-hmm. Yeah. So yeah, that's something I couldn't formalize myself. I feel there is a connection to implicit time stepping and iterative fixed point iteration things, but that I cannot really tell you, hey, this is this kind of algorithm from numerical analysis, right? It doesn't really resemble. There is a flavor of implicitness and fixed point iterations here, but in numerical analysis, we rarely take something and deliberately add noise to it. So I'm not aware of algorithms that, yeah, could be used to interpret what's going on. Yep. Yeah. If you predict the noise perfectly accurate, then yeah, I would guess you recover what came in as an input. But then in the next step, you add a new noise to it and so. Yeah, I mean, during training, you're always computing this loss against the ground truth for the next time step, right? So you're using that information. You know what the ground truth for the next step is. Yeah. Mm-hmm. No, this is UT. This is the true UT. This is the true next time step, the ground truth for the next time step. No, we're actually using the ground truth during training.
Okay.
Yeah. Well, that is also okay. So during training, we're actually using the ground truth. But during rollouts, during prediction, then there is this U hat thing that enters a picture. Yeah. Yeah. Yes. Yeah. With the same noise schedule. During rollout, you just you go to capital K. You do like 4 refinement steps. Yeah. Now the drawback is computational here because obviously, at every step you have to do your forward pass K times instead of 1 time. So this model is going to be K times slower than a plain neural operator without this refinement process. Yes, exactly. So here you see, like in the paper, we kind of did an ablation by increasing capital K, and usually after 4 steps, you don't get any more improvement. Yeah. Right. Yeah, for sure. And also the noise scheduling is more aggressive than standard diffusion models. And it goes down to really small. Yeah. Right. Okay. I think we should conclude here maybe. All right.